Hello guys, we'll be talking about the energy change and rates of reaction. So first of all, we're gonna talk about thermochemistry. Thermochemistry is the study of the heat energy associated with a chemical reaction, with a chemical or physical reaction. A reaction may release or absorb energy, and the phase change and a phase change may do the same. So reaction releasing or absorbing energy they are referred to as endothermic and exothermic reaction. Exothermic reactions are when the reaction releases energy, and endothermic reactions are when the reaction absorbs energy. And so yeah, basically that's it. And we move on to the next. The calorimetry. Calorimetry is the science and like the measuring of changes in the state variable of a body for a purpose of deriving the heat transfer associated with the changes in its state. Example, the change to chemical reaction, physical reaction, or phase transition under specific constraints or heat. Yeah. Specific heat capacity. It is the amount of heat per unit mass required to raise a temperature by 1 degree Celsius. So basically, if that wasn't clear, it's like the amount of heat you need to increase the heat of the temperature of a substance, like higher, to increase the temperature of a substance. Yeah. And calculating the change in energy, which is heat, which is represented by Q, is equal to mass M times calorie with a small c times the change in temperature, which is the final temperature minus the initial temperature. We shall look at examples of that later. Enthalpy formation. Enthalpy formation is the standard enthalpy for formation of the compound from its elements in their most stable reference states at the chosen temperature. The heat of formation is it's the heat evolved or absorbed. So it's how you An important part of studying chemical reactions is to monitor the speed at which they occur. Chemists look at how quickly or slowly reactions take place and how these rates of reactions are affected by different factors. Chemical reaction rate is the study of the rate at which chemical reactions occur. The reaction so it's the rate of reaction is represented by the change in quantity over change in time. And to find to determine the reaction rate, you have to calculate for the final quantity minus the initial quantity over the final time over the initial time. And the change in concentration of reactants or products over time is often graphed. You use two different calculations for these, so you can name them A and B. So say the product is B and the reagents are A. There are two types of reaction rates: average rate of reaction and instantaneous rate of reaction. Average rate of reaction is the change in reactants or products over over a given time period, slope between 2 points. An instantaneous rate of reaction is the rate of reaction at a particular point in time. Expressing the reaction rates in terms of, so the method for measuring rates of reaction, the volume, it's change of volume over change in time, mass change in time, change in mass. So no matter the what you're finding, you always put your property at the numerator, and then time at the change in your property at the numerator, and then the change of your time at the denominator. So we'll do some examples on that later too. So now we go on collision theory and factors affecting the rates of reaction. According to the collision theory, chemical reactions occur when reacting particles collide with one another. One of the fractions of collision between particles results in a chemical reaction because certain criteria must be met. For a collision between a reaction to be effective, between reactants to be effective, the orientation of the reactants must be favorable, and the collision must occur with sufficient energy. And for chemical reaction, reactants must reactor molecules must also collide with sufficient energy. I already mentioned that. Activation energy is the minimum amount of collision energy required to initiate a chemical reaction. Collision energy depends on the kinetic energy of the colliding particles. They're representing the progress. I'll show them later because I need the activation energy and enthalpy. Factors affecting reaction rates. Nature of reactants. Reaction of ions tend to be faster than than those of molecules. Concentration. A greater number of effective collisions are more likely with a higher concentration of reactant particles. Temperature. With an increase in temperature, there will be more particles with sufficient energy needed for a reaction. So with temperature, the higher the temperature, the faster the reaction, meaning the more collision occur. Pressure. For gaseous reactants, the number of collisions in a certain time interval increases with increased pressure, because when you increase pressure, the molecules move closer, which there's less room for moving around, so they collide with each other. And surface area. A greater exposed surface area or solid reactant means a greater chance of effective collision. In the presence of a catalyst is a substance that increases the reaction rate without being consumed by the reaction. So it's going to be 100 plus 200, which is 300 joules. And that's the idea of Hess's law. Okay, so the relationship between the rates of reaction and the concentration of reaction is expressed as by a rate law. For example, the gas phase decomposition of the nitrogen pentoxide. Okay, so this it's gonna be K equation equal to the reactants. Reactants will represent each reacted by M plus N over the product P. So it's going to be EQ equation, the concentration of nitrogen dioxide and raised to the power 4 because of this here, 4, and the concentration of dioxide, it doesn't have anything, so you don't put over the product, which is N2, well, 5 to the power 2, which is this. Yeah, so you calculate for the concentrations, and you must make sure not to confuse the equilibrium constant expression with the rate law expression. The expression for K equation can always be written by inspecting the balanced reaction equation, and contains a term for each species or each of the reaction whose concentration changes during the reaction. The equilibrium constant for the above reaction is what I wrote, this one here, that's the equilibrium constant, but the rate will be, the rate for the rate law will be K is equal to concentration of N2O5. This is the rate law concentration. Order of reactions are often classified as zero order, first order, second order, mixed order, or higher order. The general reaction A plus B to C, let me write to where there's more space, so A, capital A, B, will be this will be used, let me finish, will be used in the following discussions. First, the meanings of these orders are defined in terms of initial rate and reaction effect. Zero order, in the reactant there is no effect on the initial rate of reaction. First order, in the rate, first order in the reactant, the initial rate of reactants doubles when the reactants is double, and second order in the reactant, the initial rate of the reaction quadruples when the reactant is doubled, and the third, the initial rate of reaction increases 8-folds when the reaction is doubled. So a zero reaction has a constant rate that is independent of the reactant's concentration. The rate law is as follows: rate is equal to K, where K has a unit of m, s raised to the power K has the unit of that. In other words, zero order reactions have a rate law in which the sum of the exponents is equal to 0. The integrated rate law of zero order reaction is given below, which I'm going to write here. So concentration of A is equal to minus KT time concentration A